Hello everyone. I hope I'm audible. Can you let me know in the chat box? And we will start in a few minutes. Let's see if more people join. Thank you. Okay. Okay. Thank you so much. Yeah, sorry, I was on mute. So what I was saying is that we will get started now, and hopefully more people will join. And so first, what will be the today's agenda is first I will let's discuss that. Yeah, so what we had looked at yesterday, we looked at basically buffer overflow attacks. And like we looked at buffer overflow vulnerability first, like why it like what vulnerability exists in your it can exist in your say programs, and then the exploits also we looked at, like uh how can we do like construct a sequence of steps so as to use that vulnerability to cause a attack. So, so yesterday we had looked at this, and today what we are going to do is then look at the next class of attacks, which are return to libc and return oriented programming attacks. So these are also buffer overflow attacks only. Like these are also a type of buffer overflow attacks. And why do we want to study them? Because when we studied these previous attack types, so there were some defenses that we had talked about, right? We had talked about some defenses, like we talked about W XOR X, then stack canaries, and also ASLR, address space layout randomization. So what I will go over this part, like I'll do a recap of this part. Then we will get started with these different like these further with these buffer overflow attacks. Now these buffer overflow attack, why are we studying them? Because the previous defense mechanisms were able to prevent the previous attacks that we discussed. Okay, and so now we have to come up with new attacks. So basically it's like the attacks were first, like say, and earlier the buffer overflow attacks, like they came, so then they were of the kind that we discussed yesterday. But then we had put some defenses, and then the attacker had to try new kind of attacks which would subvert these defense mechanisms. Okay, so in security, it's always like a cat and mouse game where you will, so the attacker is going to say, come up with an attack. Then, as a security practitioner or a security, if you are a developer, you are going to try to find out these defense mechanisms for those attack, and then you're going to say patch your software with that. But then the attacker will try to subvert the defense that you have proposed, that you have in place, and will try to still say do some attacks using the vulnerability. Now some of the defenses, like these defenses, that shows that these defenses were not like able to completely uh, defend against all kind of buffer overflow attacks. And so these different kind of attacks are still possible, so that's why we are then going to look at more defenses. And those defenses that particularly we are going to talk about today are called control flow integrity and memory bound checking. So these defenses are actually uh, so these defenses will be we will study them with respect to these return oriented libc attack, the control flow integrity, and the memory bound checking will be like applicable to all kinds of buffer overflow attacks. We will also look at another class of attack, which is a format string vulnerability. Like format string exploit, basically, which is going to exploit the format strings which are there in your printf, scanf, etc. In this class of library functions. So, and later, if we will have time today, then we will look at the access control mechanisms in Linux. Okay. So this is how we are going to do, but I am going to move this here. Oh no. Uh, I was actually sharing my writing on my screen. I hope my screen is visible now. One second, I'll share it again. I think it's not able to share. Okay. Yeah, I'm sorry for that. I forgot to share the screen. And so this is what I was writing or I was talking about is that for this will be the agenda for today's uh, uh, today, like day two of the workshop. Okay, so yesterday we had looked at buffer overflow vulnerability and exploits, and then we looked at some defenses, WXOX, stack canaries, and ASLR, and then we discussed how these defenses are going to prevent the exploits that we had discussed. Okay, so these defenses were able to prevent the exploits that we were had discussed yesterday, but then but then there exists a different class of attacks, okay, which exploit the buffer overflow vulnerabilities, which are not prevented by these defenses, like the return to libc and return oriented programming, which we are going to discuss today. After that, we are going to look at the format string vulnerability in the printf and scanf library functions. And after that, we are going to look at some defense mechanisms which have been proposed to defend against these buffer overflow exploit, like this class of buffer overflow exploits, return to libc and return oriented programming. So in particular, we are going to discuss control flow integrity and memory bound checking. Okay, so we will discuss them. And if time permits, then at the end, we are going to look at access control in Linux. Now, what I'm going to do now is that I'm going to start with a recap of what we studied yesterday. So that uh, because this is a new topic for everyone, and I think a recap will help. And then after that, we are going to uh, then we are going to start with return to libc attacks. But so we will be forming this table actually. So this is so what we are trying to do here is we will try to answer this question, like, can the defense prevent the attack? Okay. So this is the question we have to ask whenever we are going to fill some entry into this table. And so this on the So this column, the first column, is your memory exploit types that we are discussing. Then these are your defenses that we have, some of which we discussed yesterday, and some we will be discussing today. Now, the memory exploit types, the first one is here is data corruption. Okay, using a buffer overflow kind of attack, using buffer overflow vulnerability. This we did not actually in particular discuss this, but I will describe this now. Then there was execute code on stack, which we had looked at the exploit, and we discussed that how the attacker can craft such exploit and then exploit the vulnerability in your program. Today we are going to look at return to libc, which is also buffer overflow exploit, and then return oriented programming also is a buffer overflow exploit. Then later today we will look at format string exploits. Basically, format string exploits also we are dividing it into two types. First, which just corrupt the local data of the program, and the second one which corrupt the control data of the program. Now, what is control data and local data? That also I will just describe now. So first, what is data corruption? So we did not discuss this yesterday, but when your when you overflow a buffer, maybe before I do this, let me actually go and look at the first. Let's do a recap, and then we will try to answer these questions. Okay, but before I start, I hope everything is now set. I'm sharing the screen. I'm on unmute and we are recording the session as well. If there is any question, then let me know. So this recap session, I will try to ask you more, and so you try to like answer as much as you can in the chat box. Yeah, so we had looked at this buffer overflow vulnerability, which exists in your program. Why does the buffer overflow vulnerability exist? Because you have these two buffers, one is destination and one is your source buffer. And you're copying from your source buffer to your destination buffer. And but when you're copying this value, you are actually not checking the bounds. You're not checking how long is your source buffer and how long is your destination buffer. So you're copying without any checks, and so because of that what happens is that you can write out of the bounds of a buffer. So you may, in this example, uh, you have allocated only 8 bytes for this buffer buff, but you're calling the str copy library function to copy the content of this string here, which we're passing here as a second argument, to the buffer here, and the string here is actually of 12 bytes. So hello world, there is a space in between, and at the end there is a \0 character, null character, and so in total it is a 12-byte string. And your str copy function is actually exploit, like it is a vulnerable function here, which does not perform any checks on how many bytes are being copied from your source to the destination, and it is just going to copy the from your source byte by byte until it encounters a null character in this case. But this is actually not a vulnerable program. So in the sense that if hello world, you are going to, because it does not give the attacker any flexibility into crafting the source, uh, into crafting this source source string. Okay, what may happen is that if you try this on your if you take this code, if you try to code it and if you try to compile it, it may happen that you will get a segmentation fault, so it may crash. But that is also a crash at when the you as a programmer is testing your program. Now what gives the attacker the flexibility to exploit this vulnerability? So that the attacker can do, if you're taking an input from, say, the user, or you're if you're reading the input from network, or if you have basically any uh, interface inside your program which is taking in outside input. Now, if the attacker can control what input is read by your program, and then if such a vulnerability exists, then the attacker can try to give a malicious input. Now, what is a malicious input here? The malicious input here would be, first, of course, it is going to write beyond the bound of the your buffer, but what is it also going to do? So maybe you can now uh, tell me in the chat box that what would be a malicious input. Like if you're writing this malicious, the goal is not just to say here, uh, say crash the program, but if you want to do anything interesting in this program, then what will be the goal? Yeah, so you want to invoke a shell and you want to create a shell. Yes, but how can you do that? So what are you going to do? How will you craft your input? Like what the does your input should take care of when you're giving this byte sequence as an input to this program? You want to create the shell, that is the goal, but what will be the steps to do so? So of course uh, you have to, in this case, you have to give a input which is of size larger than 1024 bytes. so that it is able to corrupt the other values which are there on the stack. Now, what are the other values on the stack? Can you tell me what does your stack will contain? Not for this particular example, but in general, if this is your function get user input, or any function which has this function, sorry, if this is your function which has this vulnerability, such as a string is being copied from source to destination, then what values are there on the stack which can get corrupted if you write out of the bound of the buffer? Yes. So you want to change the, we looked at that we can change the control flow of the program by changing the return address or of the previous function. Like we can change the return address and then we can change the control flow. So that's right. Another answer is that the stack contains the values of return address, eBPF of the previous frame arguments for the function. Yeah, that is absolutely right. Return address of the next instruction of the function call. Yeah, and there is one more thing which is there on the stack apart from these. We did not actually focus on that yesterday, but your stack also contains the local variables. Okay, so if you the local variables of a function are stored on the stack. The arguments to the function that you're calling stored on the stack along with the return address and the previous stack frame pointer. So these values are stored, and the attacker can actually, or by writing outside the bound of the buffer, can overwrite any of these values. Now, these values which are stored on the stack, we are going to actually, we can classify these values into two types. One type of values are going to change the control flow of the program, and we call such values as control flow data. Okay, like your return address is a control data, because if you change the return address, then you can change the control flow of the program. While your other values on the stack, such as your local variables, argument to this function, they are not control data, because if you change those value, actually those can also be control data. But let's say uh, your argument to this function, or yeah, those can also be the data, control data, if they are being used in your conditionals, like if else, uh, or if they are being used as a condition, then that data is control data. But any data which is not being used to make any to verify, like to say make a decision like where to go, it is not part of any conditional, then that data is not a control data. So your stack contains both the control data as well as the normal data which is used for computation, and the attacker has the flexibility to modify any of these data by writing out of the bound. So to so if the attacker, now I'll just ask a question, you can try to answer this. So maybe let me just modify this example here and create here one more int. So I'm here actually trying to create this example. Okay. So here what I'm doing is that to this user input function, I am passing one more parameter, which is auth value. And then I'm going to uh, set my local variable here, which is auth equal to auth value. Or we don't even need to do that. But what we are going to do that, we are going to actually, or let's just create a auth. variable. Okay, and then what we are going to do is that we are going to, okay, maybe it's better if I copy and write it on different slide. So we are looking at this example now here so that we can distinguish, we can look at some like other kind of control data. So like there are these different kind of control data in your program. One we of course know is return address. Okay. Then we are looking that now at the different kind of a control data, which is these, there are some variable, there can be some local variables also in your function, which can be used to compute some condition. Example, here auth variable can be like if the auth variable is true, that may show that the user is an authorized user. Okay, and then only the user should be allowed to say give a input to the program. Let's say otherwise the user we know is unauthorized, and then we can say print that you are an unauthorized user, and we are not going to say take the input. So we can have such a function. Okay, now although I think for constructing this, not the input actually we are going to need if we want to create this exploit, but maybe we are going to do some authorized operation here. We are going to allow the user to do an authorized operation here, and we are going to not allow it to do any operation here. So what we are actually doing here is that we are passing this function a value. The value is the auth value, which is telling whether this user is a authorized user or not. Okay. And then we are creating here a local variable auth and copying the argument into this variable. After that, we are taking the input from the user. And then based on the value of this auth variable, we are going to check whether whether the user is an authorized user or not. And if the user is authorized user, then we are going to allow the operation to happen. Now, let's say that you are going to invoke this function. Uh, so let's say that you are going to invoke this function, get user input, and you're going to pass it value 0. Now, do you think it do you think it is possible for the attacker to execute this authorized operation? I hope that this program is clear. Can you let me know in the chat box that the question is clear? That the question I'm asking is that this is you invoke this function uh, with the argument 0. Then can you think of an exploit here? You're reading the input from the user. Can you think of an exploit by which the user, although the user here is unauthorized, the user auth value is 0, can do this operation, authorized operation? Yeah, so that is right. So you got this right. So since what's going to happen is like most likely you your this is your local, like this is your function, right? For this function, the stack frame will be created. Yeah, so we can fill the buffer and then we are going to 1024 bytes we can write, and then we can write at the end we can write 4 bytes, like because it is an integer, so it will be stored in 4 bytes. So after that, we are going to write a integer value 1 in 4 bytes. So, so here, but for that, we may have to inspect the stack, like the how the stack is layout as well. If so, but your compiler is going to add code here to allocate space for this auth variable, also this buffer. And earlier, we had actually not looked at any arguments, sorry, any local variables. But here, let's say when we create this, yeah, basically, if let's say this is your function which is called get user function. So imagine that this yellow box is now for get user function. Then this get user function yellow box here will have space here for auth, and then there will be for the buffer. So now coming back here. So as you said rightly, that then we will be able, because the auth variable is also stored on the stack, and if we write out of the bound of the buffer, then we can change the value of the auth variable to value 1 by giving a crafted input, and then we will be causing the program to take this branch, even though originally the auth variable was 0. So this is also a control flow attack, right? But in this, we are not using but in this, so this is a control flow attack, right? And this, we are doing this by changing the value of a variable. So here, auth is also a control data, and we can say it is a control variable, control data variable, because it is being used as part of conditional check. Next, can you think of any other data in your program which is also used to as control data? Like basically, it is used to determine where to go. Yeah. So the next type of control data is your function pointers. So, so function pointer. So at runtime, so the function pointer values are actually, so they will be. So if you do a call to foo, and if you say foo, and then if you call it, then the where is that function located? That is actually determined at compile time only. The compiler itself knows that where is that which function you're trying to call. But if you have the function pointers, like if you're calling a function through pointer, so then it the compiler may not know that actually which function you're calling, right? Because that function address is going to be, it is possible that you can change that value, the value of that register, which is containing the address of the function at runtime. Like say, like for example, say your function is foo, and you are going to pass it, say an argument int a, and after that you're going to pass it a function pointer. So it is possible that you can once call foo with 1 and then pointer to bar, and then next time you can call foo with pointer to say foo bar. So these function pointer values, they are dynamically at runtime. The compiler doesn't know that where you want to actually change the controls, where you want to, which function you want to go. And these values are also stored on the stack. So this value is also going to be stored on the stack. These are also either local variable or arguments. And this also gives you the attacker the flexibility that to change the control flow of the program. So if the attacker is of course, if the attacker is able to find out where this function pointer is stored on your stack, then the attacker can use the buffer overflow vulnerability to go and corrupt the function pointers. And again, that also can change the control flow of the program. So these are different ways in which the control flow of the program can be changed. Okay, you can the attacker can change the return address, can control the data variable, can change the function pointers. Yesterday, what we had looked at was changing the return address. And I think, and in one of the example during the class, actually, we had also looked at the changing the data and then changing the control flow of the program. And I think uh, some of you were able to run this program and see that it was able to skip the instruction. So this was a data in your no, actually, this was not data. It is actually pointing to the return address. So yeah, so all of the examples that we looked at yesterday, they were actually changing only the return addresses. But maybe you can try this later if you're interested, that you can change these other kinds of values also on the stack and therefore change the control flow of the program. Next, what we had not discussed was that the buffer overflow exploits can be used to change the other data also on the stack on your other data of the program, like some other variables which are not at all used in your uh, control flow. So if the data is not at all used in your control flow, then that data, like non-control data basically, and if the attacker writes beyond the bound of this buffer, then that data will be corrupted. And finally, your computation, which is being spit out by your program, that computation output can be wrong. So even though your program the overall control flow of the program might not change, like you may not have executed another function, or you may not have changed any data variable to change the branch of and the condition of any branch instruction here. But what is possible that you may have changed the output of the program. Okay, so if this variable was not just, let's say some data is here and it is like, for example, just let's say uh, let's say this is uh, I mean, just only for the purpose, for just example purpose, let's say this program also has your account details. Okay, I am not sure how to, I hope this is visible, and let me try to um, like, I'm just giving this as an example. It's possible that you may not find this in real world, but let's say this is your, something like this is your program. Okay, and let's say the it has a variable which is like account amount. So this is the amount in your account. Okay, and let's say you are passing hit year, the user ID, or like whatever. So this is your function, and it has here a variable which is representing the amount in the account, user account. So it is currently set to 1,000. Okay, or maybe there is some value, but currently I'm saying that it is set to 1,000. Now what the attack, if this program here, if it is taking input from malicious input, if it is taking an input from the user, then the attacker can provide here a byte sequence such that it can write beyond this buffer and thereby corrupting this variable which is storing the amount for that user. So it can go and change this to any arbitrary value that it wants to change it to, right? So it, in this way, it has not actually changed the control flow of the program, but it has changed some data in the program, and that data can cause the computation of the program to get corrupted, and therefore the data which is being generated by your program may no longer be a uh, reliable data. So I hope that is clear. If not, please let me know. Okay. Is there any question? Okay, so there is no question. And then I'm just going to recap this layout of the stack that we had looked at yesterday. So we looked at their two function main and foo in this particular example here. Okay. And the foo is main is calling foo with these three arguments, 1, 2, and 3, which are going to be. Now let us see. This is the bottom of the stack. This is the top of the stack. The stack grows downwards, okay, always. And then EBP is your frame pointer, which is pointing to the start of your stack frame for that particular function where the program is currently executing. And the ESP is the top of the stack. And when you are going to call foo from the main function, then the arguments to the foo are pushed onto the stack in the reverse order. So like 3, 2, and 1 will be pushed in the reverse order. And after that, you're going to push the value of return address, which is the address of the next instruction after foo. After that, you're going to push the value of previous EBP. That is the previous stack point frame pointer. And after that, you're going to set the value of EBP equal to ESP. Now, with this, we have created a new stack frame now. So now the stack frame for foo function will start from here, and it is pointed to by EBP. Now, if you have these variables, local variables in foo, then the space for the local variables will be then allocated in the next few instructions. So to allocate the space, basically, you are going to decrement the value of the ESP and say this is space has been allocated for these two local variables, buff1 and buff2. And then these are located here, say. And then we had looked at these two instructions, leave and ret, because these two instructions are going to uh, going to they're responsible for returning from a function. Okay, so leave is going to restore the value of the EBP, which is stored here. Okay, it is going to set the value of EBP equal to this value stored here, previous frame pointer. And return instruction is going to take the address from the return address from the stack and then going to change the program counter to point to this return address. And since this, so we had then looked at that so then we looked at that if we are taking a user input and if the user input is beyond the bounds, then the user can then the input can corrupt the return address which is stored here and thereby changing the control flow of the program. After that, we had looked at a shell creation exploit. And after that, we looked at the defenses. So now here, can you tell me, so we just talked about this attack, right? Data. So we just talked about this attack where the attacker can corrupt the non-control data which is stored on the which is stored on the stack, such as this amount variable. Now, can you tell me whether W XOR X can prevent such attack? So is this So yes, asking just changing EBP, ESP pointer values is enough because the variable values are still present at the bottom. So those variable values are basically no longer, so when we are returning from that function, so we are saying that the function is no longer executing. So we're returning from there. So those values are not going to be used by the function where we are returning to. So in that sense, it is okay. But yes, if some values are stored there, and if those values are say, uh, if those values are say confidential, then we can do a read of those values because we are not changing, setting them to 0 here. But the values were local to the function. So the values what we had stored here, like the buffer here, is actually local to the function foo. Okay, so you cannot even access this from main. Like it has no meaning as such in main. Otherwise, so that because this foo buff is not going to be used in the main. So even if you go and change anything in the buff, let's say by doing ESP minus something. First of all, that is not possible with this buffer overflow attack here. Why is it not possible? Can you tell me that if you are main function and the buff is here, and if the main has this buffer overflow vulnerability, can you go and change the buff here, even though we have moved up? The arguments are confidential to whom? The main is passing the arguments. The arguments are being passed to who? So both of them knows the argument, right? Main is passing value 1 to 3. Main knows the value 1 to 3 and pass to foo, and the foo can read them. So they are not confidential with respect to these two functions. But what you're saying is the variable is still present at the bottom, but the variable scope has actually finished. So this variable was local to function foo, okay? And the scope of this variable was only limited to this function foo. That means that this variable was used only in this function foo. It is not even going to be used in this function main. That's the first part. Second part is even if there is a vulnerability, buffer overflow vulnerability in the main function, you cannot actually go and change the value of this buff, which is stored here, even after you return from foo. Now, I'm asking, why can you not change this memory addresses? Why can, like, let's say this is your buffer overflow. Let's not talk about in terms of main. Let's talk about in terms of foo. So this is your buffer, which is located here. Can you use the buffer overflow vulnerability to change any values which are below the buffer here? Now, how can you change? How will you change? So this is your buffer, right? I'm talking with respect to the function foo. In function foo, we have created this local buffer, buff, which is located here, okay? And you're going to take input from the user and you're going to start writing into this buffer. Now and that is the vulnerability that we are talking about, buffer overflow vulnerability. Now the question is, can you exploit this vulnerability to change anything down in the stack below the start address of the buffer? Yeah, so that is right. The writing is going to take place upwards. Okay. So first, we are going to write upwards. So as you can see here, when we start writing, the stack is growing downwards. But when we are writing these values, we are writing them in upward direction. So addresses are increasing. Okay. So that's why we are writing in the upward direction, starting from there. Here, this is the start address of the buffer. We are going to write upward. And that is why we are able to corrupt these values like return address. But we cannot use this vulnerability to write down in the stack. So since we cannot use it to write down, or then we cannot even use it to read down. Okay. So we are not able to use a overflow vulnerability to either do a read or write or down in the stack. Yeah, so even if you're calling some other function and that function has some other confidential data, when you return from that function, then you cannot use this particular vulnerability to access the data which was present on the stack for that function. Because with this vulnerability, you cannot, if you are writing only above on this stack, your writes are happening above, and your reads are also going to be like above. Like with particularly this, if you're passing an input, you're going to actually just write from starting from here, and you're going to write above. But yeah, of course, if you are in the main function and if there is an array, if you allocate an array here, and then you have the address of that array, so basically you can uh let's say that array is allocated here and you have that address, you can of course go like to the address minus 4, then you will be able to read the next bytes. Then you address minus 8, then you will be able to read the next 4 bytes and so on. So you can definitely read them or you can maybe change them, but that is not like using this vulnerability where we are reading the input from the user. And of course, the vulnerability there is still also that we are able to access out of the bounds of the array or the buffer that we have allocated. Because there is no check which is happening in the C program to check whether you are accessing the data out of the bound. So think, okay, so I hope that is more clear now. If you have, if it's still not clear, then please ask me again. I can even unmute you after like in the break session, and then we can discuss this later again. Uh, so now this is okay. I think I should quickly wrap up this and start with the next part. But we, so let me just So yesterday we were able to then like create this shell. Okay, we were able to put a code onto the stack, right? Uh, like here in this buffer, if we are able to put the shell code, and then if we modify the return address here to point to the start of this buffer, then when the function returns, then it will start reading from here. Okay, so this will be the next instruction pointer. It will start reading the instructions from here, and then it will invoke the shell. Now, so we were able to invoke the shell. And then we argued that there is this defense mechanism, which is W XOR X. And if we implement the W XOR X defense mechanism, it says that your pages can either be writable or executable. So the stack pages are no longer executable, means even if the attacker is able to put any code on the stack, the attacker cannot change the return address to point to this code on the stack. And therefore, we were able to prevent this kind of an attack. Now, today we are going to look at, but see, now we are going to look at the other class of the attack, where even if we have this W XOR X defense in place, we will still not be able to prevent a buffer. We can still craft a buffer overflow exploit, and which will defeat this W XOR X defense mechanism. So later, actually, what we are going to do as an exercise, I am just, before I do this, I don't understand. One second. So I don't think I have that slide open. But what we are going to next, like later, we are going to compare. Like I was showing you earlier that we are going to create this table where we are going to have these different kind of exploit, and we are going to have these different defense mechanisms, and then we are going to make this table, and we are going to check whether a defense is able to prevent that particular class of attack or not. So now today what we are looking at is this return to libc attack. And the question we are asking is that will non-executable stack prevent the buffer overflow attacks or not? Now, what does come to your mind when you hear this term, return to libc attack? And the motivation to do this is actually we want to bypass the non-executable stack during exploitation. So what does come to your mind? Where are we returning? What does this mean? System calls. Yeah, in effect, that is system calls. But a program actually directly does not call the system calls, does not make the system call. That program that you are writing directly usually do not make a system call. The library functions are going to make the system call. Yeah. So we are going to execute the functions from the libc. So return to libc. We are going to change the return addresses here so that we are able to invoke a function in the libc. Yes, that's right. So libc is a dynamically linked library which is linked to almost every program in your whenever you compile a program, it is linked to almost every program. Okay. And if you will, even if you will write a very simple program, hello, and which is only printing hello world, then if you will compile that program, and if you run that, if you compile that program, and if you are going to run it, and if you then go and check the virtual memory map of this program, then you will see, which you can do by uh, for that you will need the PID of this program, and then you can run this command sudo cat /proc / the PID of this program and /maps. So this is going to give you the list of the uh, virtual memory maps in this program, and you will see there that the libc library is also has been linked to this program, and this is the virtual memory address range where the libc is mapped. Okay, so the libc library is actually mapped in almost all the programs, and Now, in return to libc attacks, what we are going to do is that we are going to replace the return address to point to a function within the libc. So when we have this buffer here, then we are going to start writing into this buffer, and then we are going to start writing here the address of a function in libc, like f1, 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 f1. And we are going to write it everywhere, or every 4 bytes, we are going to write this address here. And say return address is stored here on the stack, then that return address will be changed to the address of this function, which is somewhere in your text segment here. Now, this bypasses the W XOR X defense mechanism because F1 is in the code segment, right? It is part of the code segment. Like if you will actually look here, so this is the virtual memory address range where it is mapped. These are the permissions on these memory ranges. So this is the permission. So if you see, then there is XXX. That means the library pages, the memory pages where the library is mapped, those have executable permissions, right? And so here in this particular, the stack is also executable, but if we can disable that, okay, we can make it non-executable. Then, since this is part of your text segment and it is executable by default, and so if you will change the return address to point to this function, then you will be able to invoke that function. And this will circumvent the W XOR X defense. Now, what can this function f1 be? So one option for this function is the system function, which is present in libc, which will take a string value such as bin/bash, which is actually the executable. It is representing a executable, and this function is going to take this, and then it will start this executable. So in this case, if you pass it the string /bin/bash, then it is going to create a bash shell. So what do we need to do this exploit? So to do this kind of an exploit where we want to change the return address on the stack to the address of the function f1, where the function is system function, we would need the address of the system function, right? Like last time we were changing the return address to point to the address of the shell code we had written on the stack. Now we are going to change the return address to point to the address of this system function in the program. So for that, first we will need to find the address of this system function in the program. Second, we also need to pass an argument, right? Here /bin/bash. So then we will need to write this string. We will need to pass the address of this string to this system function. So we will have to change the return address, and then we will have to put the argument also on the stack. So let's now look at like how to do so. So we are going to change the return address here to the address of the function that we want to invoke in libc. Here we are invoking this function system, and the system function needs only one argument, which is a pointer to a string. So it's a pointer to a string, and then we are going to put the pointer to the string here, /bin/bash. So then what will happen is that the program, when the program will return, then the program is going to take this address here, and then after that it is going to take this address from here, and then it will start executing the from here the system call function. Sorry, not the system call, the system function in libc. Now, if you will notice that we did not actually put anything here, and we are putting the so we have say located the address of the string /bin/bash. So the string actually already exists somewhere in your program, and you have found the address of the string, the null terminated string, and you have put the address of the string here. So is there any question so far? Okay, so just to reiterate, what we are doing here, we are changing the return address, but we are changing the return address now not to point to a function in libc. And if that function takes some argument, then we have to put those arguments also on the stack. Currently, here in this example, we are calling function system, which is going to take only one argument, which is a pointer to a string slash bin slash bash. So it's a pointer to a string slash bin slash bash. And you have, say, found the address of this string. Okay, it is there as part of it is somewhere in your program, and you have found the address of this string, and you have put the address here. So then when your program is going to return, it is going to pick the address from of the next instruction from here, and that will be the address of the system function. And then when you start executing the system function, then it is going to pick up the arguments from the stack, right? That's how a function would work. Now, can you tell me, like, why have we like not put this argument here, but the argument here? The stack is always okay. The question is, to defend against this, can't we make return addresses non-writable? Does WXR is not it already? The stack is writable. So the stack is always writable. Like we cannot make only I mean, there is no way that we can make, like, say, choose to, that this particular byte on the stack is going to hold the return address and then make them only uh, non-writable. Also, the permissions that we set for this for when we set these permission, writable, executable, etc., then we do them at the level of memory pages, which are usually like 4 KB pages, and we set the permission for the entire page, that the either that page is readable, writable, or executable. And the stack has to be writable, because we are storing the creating local variables, calling new functions. We have to create new stack frames and store variables. Now, the question that I'm asking here is that this 4 bytes, we have not, so basically here we have not written anything. We have written the string address to the pointer, address of this string slash bin slash bash, which is the argument to the system function here. And the question I'm asking is, why have we left this gap? Yeah, so that is right. So if normally when you would call another function from a function, you're going to first put the argument, then you're going to put the return address, and then you are now then after that the call instruction. So this is done by the call instruction, right? First you are going to push the arguments, then the call instruction is going to put the return address, and then the instruction pointer is going to change. So to mimic that, let's say that this particular, like, for a while, just forget that this is even here. If this were just a normal call to this system function, then you would have first put the address of the string on the stack slash bin slash bash, the address to the string. Then you would have put here the return address where you want to return to after the call to system, right? And so when you are going to call system a function from here, it is going to expect the stack in the same way. It is going to expect that there is a return address here. And that's why you're putting the argument here. So I hope that is clear. Now, how do we find the addresses of these two things? So we need the address of the function system, and then we need the address of this string slash bin slash bash. And so what we are going to do, that for that we will use GDB. Okay. And then in GDB, we can use this particular command p system. So this is going to give us the, this is print, and then we are saying that give, like, we are asking it to print the system, to look for this variable to look for this, like, particular this name system, and then it is going to print where it can find this string. So it spits out here that this string is located here slash sorry 0x280 85260. So that means our system function is located here. Okay, actually, so we are going to look at this in the demo also. After that, we also need the address of slash bin slash bash. So currently what we are doing is that we are looking at the steps that we need to create this return to libc exploit. So we have found the address of the function that we want to call in libc. Now we want to find the address of, like, this function is expecting a address to a string. So here we are trying to find that does the program already contains this string slash bin slash bash. So the every process actually stores some environment variables and at the bottom of the stack, and in that environment variable usually there is like this shell variable, and this will have your shell, which shell is being used by a program. So then the shell variable here is set, and we just need to find the address of this variable, and then we can then pass that address to as a argument. So we find the address and then we pass it that as argument. So let's say that this is the address of that string, and this is the address of the system function. So then your stack will be laid out like this. You have the return address here, you have the address of this string slash bin slash bash here, and in between you can actually write any garbage value also. But when you do this, then your system function will be invoked, which is going to start the shell. And then, as we had seen before, when you create a shell from a program, then the shell will have the same privileges as the privilege of the user to whom that program binary belong to. So if this uh, this program binary was from user Alice, then the shell will be created with user permission Alice. So it will have all the privileges of Alice. Next, if you want this program to, if you want that after all of this, the program can exit cleanly whenever you want to, say, shut down the, say, when you are done, and if you want to exit from this shell, and after that, when you return back to the program, and if you want to exit cleanly, then here you can find the address of the exit function, and then you can write the exit function address here. Because in the previous, if you will return exit from this shell, then it will treat this as a return address, and then it will give a segmentation fault that this address is invalid. But if you put here the address of the exit system call, not the system call, so exit library call, then this is going to exit cleanly. Now the limitation of the return to libc attack is that is it provides a limitation on the attacker, in the sense that the attacker can only use these certain library functions. Okay, and the library functions can be, say, removed from the library also, and it depends on this library, so whether the library is linked or not, although the library libc is almost linked in all of these program usually, but still it puts this limitation uh, on the attacker, in the sense that the attacker can here only use the functions which are actually present in the library by default. Okay, like the system function. But if the attacker want to do something else apart from what the library provides, then this does not give the flexibility to the attacker to do anything apart from what the library functions can do. So that is the limitation of return to libc, and that's why we then next look at the return oriented programming. So return oriented programming basically gives the attacker more flexibility. Okay, and we will look at it in a while, but before that we can actually take So if you have any question, then you please ask now. So slash bin slash bash, that is the address of your, that is the string, right? And what is that? That is the address of this shell. Bash is the shell executable, and this is located at this address, slash bin slash bash. So when you are actually passing the address of the executable that you want to execute, so here we are going, when the system function sees this, uh, takes this as the address of the executable that you want to start. Slash bin slash bash is the address of the executable and it will be started, and that is going to create the shell. Bash is the shell here. Okay. Return address is in between value eBPF also. So the value eBPF is not there actually. And because the why is the value eBPF not there? Can anybody answer that? One second. Hmm, so let me just see. One second, I'll share. So yeah, I think the question is that here in between we have only the return address and not eBPF, because we store the frame pointer also. But if you recall, the frame pointer, previous frame pointer is actually stored by the function we are calling. Okay, so that is part of the function prologue. In the function, if when you're calling function foo from main, so main is going to push the arguments on the stack, it is going to push the return address, and then it is going to transfer the control to the call instruction, is then going to transfer the control to the starting of the foo function. In the beginning of the foo function, we had looked at yesterday that there are these two instructions: push EBP and then move ESP to EBP. So those two instructions are then going to push the previous frame pointer on the stack and then initialize the current frame pointer to point to the top of the stack. So that is basically creating new stack frame for this function foo, and that is done in the function foo. Okay, that's not part of the main, and because that is not part, like basically then we what we are saying here, that we are this system function will think of it like that the system function stack frame is starting here. Okay, starting from starting from here, and this this value below the string pointer, that is going to be this value here, this is going to be actually the return address that it should return to. But the value here, EBP value, would have been placed here only by the function that is being called, that is the callee, not by the caller. So I hope that's clear. So is that clear? Okay. If there is any other question regarding to what we have discussed so far, then please let me know. And otherwise, let's take 5 minute break. And after, I will like use that 5 minutes to push the code for the today's demo, and then we will look at the return to libc attack demo. Okay. So give me 5 minutes, and then we will start. Okay, so I've put the demo folder on GitHub, and you can clone it, and then you can also try these demos. Okay, so let's take a small break till 11:30, and we will then come back and then start with the demo. Okay. Yeah. Hello, everyone. I hope everybody is back. Yeah. Sorry, I was on mute for some time. Um, let's now start looking at the demo for return to libc, and we have already looked at in the slides like how we will what be the steps that are needed, but I will just go over them once more, and then we will try to look at the program that we have created with that exploit. Okay. So let's look at the steps. And the steps actually, I hope you were able to clone it. And then the steps I have written in this readme.txt. And these are the steps for doing return to libc attack here. The first step is to find the location of these functions the which you want to invoke. So first part is to actually find the return address. Okay. And not the return address, sorry, to find the location of the return address. Okay. So that is the first step, is to find the location of the return address. So where on your stack this return address is located. Like you have this buffer which was allocated, right? But how far is your return address on the stack from the start of this buffer? Because then you have to write that many bytes, and after that many bytes into your buffer, and then you have to write the return address at to write the return address at the right location. I hope that is clear. Uh, I'll just explain that in the code with the stack. Okay. So for this, for finding exactly at what at stack address your return address is located, we can do this, of course, by trial and error, as we saw yesterday, that we can try to give this program inputs of varying sizes, and then we can see at what input the program is crashing, and the program will crash when the return address is modified. Or we can disassemble the program and use GDB, and then we can inspect that how much byte has been allocated for the buffer, and what other values are stored on the stack, and where is this return address located. This we had looked yesterday how to do this. Then, so this first step we have to do for return to libc, which is same as before. The second step is to find the location of the libc function which we want to invoke. Here we want to invoke the function system, so we have to find the location of system function. Okay. For that we are going to use GDB. Again, now how do you find the address of a function? So as we had looked at that, we can here use this print command, and then we can pass the name of this function system. So when we will do this, then it will it will output the address of this system function. So when I was actually trying this demo, that time I had noted that the system function was located at some address. Okay. Then after that, so this actually you will have to make a note of, because you're going to use this to craft your input, or you're going to use this to craft your exploit. Okay. After that, you also need to put the arguments on the stack for this system function. And in the case of this system function, it takes only one argument, which is the address of the executable that you want to execute. So here, the address is actually passed as a string, and the string here we want to invoke is this shell /bin/sh. We want to invoke this shell. So we are going to find the location of this string in your program. And so for that also, that we are going to use GDB, and then we are going to find the a memory map of libc, like where in your program is libc located. As we were saying that if we can look at the virtual memory map of a running process, and for that we can either use /proc/pit/ the maps command like look at that file basically, or we can use this command in GDB info proc map to inspect, to check where this the maps of the like virtual memory map of a process. Now when corresponding to libc, so the libc library is actually mapped in certain virtual memory ranges, and these were the memory ranges corresponding to that. Okay, after that, now what we have to do is we are going to try to find the address of the string in these memory ranges. Okay, and so to do so, we are going to use this find command in GDB. So the find command takes these three arguments. First is the address of the starting address. The second is the ending address, and then the string that you are trying to find. Okay, so this is going to try to find this string from starting from this location till this location, and the start address is this address here. And as we can see that the libc is actually mapped here, starting from f79 f7d9 f000 to then here 400, then from 4000 to 5 and so on till this F7 8000. So we have given this as the start address and the end address and then the string. And then it is going to give us the address of the string. Then we can check whether the string is actually present as this address or not. For that, we can use the command X and we can give the address. And then as we were using last time, the same command, right, to print the stack content, where we were giving X comma 32X, where we were saying that, and then the address top of the stack, uh, address of the top of the stack. Here we are giving the address of this, which we have got with the find command, and we are using X, and then we are using here S. Now S is going to signify that we want to print the string. So it is going to print the byte sequences until it encounters a null character. So it's that. After that, we are going to create the payload using these two addresses that we are going to note, and of addresses in the libc, and then the address of the libc function and the address of the argument. And then we can pass this payload to the program to invoke this function system with the argument as /bin/sh to create a shell. So these are the steps. Now we are going to open GDB and then we are going to see this. But before doing that, uh, yeah, we are going to just open GDB, and so this program, let's look at first the program itself. So this is the program with the exploit. In your Here you will find two programs. One is this test2c. It is actually benign program. It is not doing anything. It has this copy buff function which creates a buffer, and then it copies the source buffer, like the source string str into this buffer. And here in the main, we have created this buffer which we are passing to copy buff function. Okay, so that's the benign program. And then we have created the attack vector in this addr.c file. So here again we have the copy buff function, but now in the buffer we are not the buffer we have initialized with this particular sequence of bytes. Okay, where the first 76 bytes are actually just garbage bytes, which we have set to a letter character A. And after that, we have the address of the system function. So this is the address of the system function. This again is some garbage, right? We had seen that it is like the return address of the system function. And this is the address of the /bin/sh string. And we find these addresses using GDB. Now we have already actually pre-compiled this program, and I'm going to use this program with GDB. And when we are going to run this with GDB here, and let's give the command R. So when we give the command R to this program, like basically when we run this program, then this program starts the shell. Okay, this has started the shell, and then we can run the command line, the commands on this command line. So now let's look at the steps to do this. Also note that here, when we exit from the shell, it is going to give us a segmentation fault, because we the return address it is going to read from the stack, it's actually a garbage value. We have put there, I think, BBBB, which is a garbage value, which is going to be read as this 42, 42, 42, 42. And so it is not a valid address, so it gives a segmentation fault. So now this is our source file, okay, and this is our exploit. Now, to do a exploit here, the steps that we just looked, let's do those one by one. So for that, we will first have to run this program, right, to look at these things. So what are the steps? The first step is to find the location of the return address, right? So first we have to find the location of the return address. So let's put a breakpoint on, can you tell me now from this, I want to find the return, I want to find the location of the return address on the stack. So what steps will I need? Like, not the steps. Can you tell me where should I put the breakpoint here? You can tell a range, like where, on which line number can I put a breakpoint here to find the return address location, like where is the return address stored on the stack for the copy buff function, like where we have to return. The copy buff function is called on line number 26 here, and when it is called, then the return address will be pushed onto the stack. Now we want to find the address of this location of this return address, so where should we put the breakpoint? 25. Okay. And so when we put on the, if we put a breakpoint on line 25, then where will we be? We will be in the main function, right? We will be in the main function. Let's put a breakpoint on 25 and see. We put a breakpoint, then we're going to run this program. Okay, then the breakpoint will happen. Now let's see, where are we? So we are going to do a disassemble. I think I will have to start it again. Whenever we start a shell, then the GDP is not able to read work properly. So let's start it again. And so we just discussed that let's put a breakpoint at line number 27, sorry, 25. And then we are going to, oh, 26. Okay, line number 26. So first let's run this. We are going to break point at line number 25. Then we can do a single step. So we are currently here. So yeah, I mean, you meant line number 26, but usually for every line of code, there can be, let's say, so many assembly instructions. So we are somewhere here into our like assembly code, okay, at this line number. So we are above the call instruction. Sorry, this is the call. Yeah, so we are above the call instruction, which is here. The call to copy buff is here. Okay, and then let's say breakpoint at 26, as you suggested, and then we are going to continue. So if we do a breakpoint here after 4 from breakpoint at 26. So if we do a breakpoint, when we added actually a breakpoint as 26, what happened was that the call has happened And so we have been able to actually execute the copybuff function, and then we have returned back from the sorry, not returned back. We have been able to we have actually successfully called the copybuff function, and so we have invoked the shell. So here what we are going to do is, what we want is actually we want to inspect the stack when the copybuff function is actually executing. Okay, because we want to see where the return address is placed, right? So that's why we are going to put a what is it called? We're going to put a breakpoint somewhere here, like line 5, 6 or something. Not even on line 7, because then it is possible that the string copy function would have executed. So we will put a breakpoint at line number 6 here. Okay. And then we are going to run this program. So now when we've put a breakpoint at line number 7, let's see what happens. So the call has instruction is executed and it has passed this string that we had. And now let's look at this disassemble it. So if we disassemble it, we are now in the copybuff function. Okay. And also let's disassemble main and see the call to copybuff. So this is the call to copybuff. And so if this is the call to copybuff, can you tell me what will be the return address after that should be pushed on this call instruction? Yeah, that is right. So the address of the next instruction will be pushed onto the stack, and here it is 484FC. So this is the call, and we will put the return address as 80484FC because the call would have executed and then we return to the next instruction. Okay, so let's remember this address. Okay, it is 484FC, and then what we are going to do is let's say, so currently we are in the copy buff function. Okay, currently we are somewhere. So now let's look at the stack. So for that, like I'm sorry, x slash 32x solar ESP. So what was the return address? It was here. So this is the return address 80484FC. This is the return address 80484FC. Okay, and this is located at some like DEA0. This is A4, E4. This is E8, and this will be EC. So this is located D2 EC. This is the address of the return location of the return address. Now, if you look at the disassembly of this copybuff function, then you will also see that it has subtracted the ESP by 44 hexadecimal value, which means 68 bytes. So it has like here subtracted this for the buffer, and the buffer that we are allocating here in the example in it's 64 bytes, okay, and it has allocated here 68 bytes. After that, it has also allocated some 8 bytes for something else, and so on. So here, on your stack will be your size for the buffer, which is 64 bytes. Okay, and this is your EBP previous EBP value. This is your return address. This is your previous EBP value. And let's look at info locals. This is your buffer. This is your address of the buffer. Yeah. So this is your starting address of this buffer, which is here D2A0. Okay. So this is your starting address of the buffer D2A0. And okay, this instruction has not executed yet. So it has only allocated space for your buffer yet. And this is the top of the stack. And this is your buffer space, which has been allocated for a buffer, which is 68 bytes here. Then after that, there is 4 bytes. No, sorry, it's not 68. Yeah, actually, sorry, this is 68 bytes for the buffer. This is 4 bytes, and then there are 4 times. So 4 4s are 16, then 16 4 64, and then plus 4 48. So this is your buffer, okay, the highlighted portion. But it has also pushed value EBX here, which is here, and then there is EBP and then your return address. So starting from the buffer start address to your return address, it has 76 bytes. Okay. So 76 bytes are there in between the buffer start and the return address. And so we have to write these 76 bytes. We can write them with garbage. And then we are going to write here the return address. Replace this as return address. After that, we can write this 4 bytes as garbage again. And then we have to put here the address of the string. So let's make a note of these. So what I would. So this is your return address here, and this is your and then like you have to put the address of the string here. So let's now see where we are. Yeah, so we are currently here. Let's now execute this program until str copy is finished. Okay, and then we will see at look at the content of the stack again. And let's make a note of this, although it's not needed, but this is the buffer start address. So after this, let's execute these instructions. 1, 2, 3, 4, 5, 6 instructions. Let me just 5 instructions and then the symbol. We are here. Okay. And then execute. Let's look at the step. It's not executed yet, actually, but yeah. So this is your stack. The str copy is not executed yet. The str copy will call other will be called, and then there'll be more sequence of steps. So that's why let's put a breakpoint at the address after the call to str copy, and then we can continue. And then if it is a symbol, we are now here. So we have executed the str copy function. So it would have copied the content of the buffer, source buffer to the destination, like the buffer which we have allocated here in the copy buff function. And now let's inspect the content of stack. So if we look at the content of the stack, it has been changed. Okay, so we have copied into the buffer. So the buffer was starting at this address FFFFD2A0, and it's starting from here. And we have copied 76 A's here. Okay, this is 76 A, like 76 bytes we have copied. After that, this was the address of the return. This was the return address in the main function, which we have now changed. Okay, and then we have put some garbage, and this is the address of /bin/sh. Now, where are these addresses? So let's so this is what I'm doing is actually sort of reverse steps, but they should have been actually in the forward direction, but I am doing here reverse. So this is address of system, and this is the address of /bin/sh. Okay. I mean, when we are going to create this exploit, then you'll have to do the steps that I'm going to show now first, of course. But I had started doing this in this fashion because we wanted to see that how many bytes we have, how many bytes are there in between the start of the buffer and the return address. Now, where is this system function? So we can find out by using p system. So it will print the location of the system function, which is this F7DDC3T0, which is here, uh, is what we have put as the return address. And after that, we also need the address of this string. So what we had discussed that for this, we will need to look at the process memory map. So this is the process memory map, and you can uh, print it with this command info proc map. And this is the start address virtual. This is the start and end virtual address range. This is the size and offsets, and then these are the object files which are mapped. Okay, and so if you will see here, these are the library libc. So this is your libc, which is mapped in this memory range here, F790 F00 till this F7 D00. So 8000. So we are going to look for the string here in this memory range. Yeah. So then this is the address where the string is located, and we can then print with this address that what is there on this address. So this address contains the string /bin/sh. And we have put this address here, which is the argument to the system function. So this is the address of the system function. This is the argument. And here we have this garbage. If we would change this to the address of the exit system call, sorry, exit library function, and then we can cleanly exit from the system, sorry, process. Let's now run this. And if we, sorry, if we continue running this, then the program is actually going to start a shell here. So now, if there is any doubt, then ask me if there is any doubt in the demo. Otherwise, you can also, the code that you have cloned from the GitHub repository, you can try that out. You can just try the pre-compiled binary with GDB and see if it works. It may or may not work because because these library functions might be mapped at different virtual memory addresses. And so you may need to, or the buffer space which is allocated might differ. So basically a binary might differ. It may not work, so that you can then try to do these steps and try to figure out why is it not working. And we can also see here, uh, just a clarification, the system address is placed in place of return address. Yes, that's exactly right. So we have replaced the return address with the address of the system function, because we are now trying, so when now this return address will be picked on by, when the on the function return, it will change the program counter to the address of the system function, and then the system function will start executing. And we have also placed the argument to the system function on the stack, which is the /bin/sh address of the string, and which is placed here. So this return to libc attack here is actually, it should work, like it will work even if the uh, z. So earlier what we had seen yesterday, that if we enable exact so basically if we enable the protection w XOR x, so that no longer the stack is executable, then our previous exploit, like create a shell yesterday, that was not working. Okay, that would not work. But if we, even if we enable the execute, even if we enable w XOR x defense, then this exploit will work. And you can also check that. And in particular, actually that is enabled by default, that would be enabled by default here. uh, in for the demo purpose, yesterday we had disabled it with -z exec stack flag. Now the question that I may ask you is that, so the stack canaries we had discussed about yesterday, do you think the stack canaries can prevent the return to libc attack? So I will ask these questions here in the discussion, and you can answer. Uh, so you can add your answers here and see. Okay. Now, okay. Please add your answers in the Q&A. I hope you can access the Q&A. So I encourage everybody to do this exercise. Just think about the defenses that we discussed yesterday. And now think about the return to libc attack we just discussed. And to think whether the defenses we discussed before can prevent the return to libc attack or not. Okay, so I think there is a little confusion about the stack canaries, and so maybe I should go over that once more. It's actually with the I think it's think can still be done. Does W, so let me go over the questions one by one. So the first question is, does W XOR X prevent return to libc attack? So the W XOR X, what is it going to do is that it is going to make the stack non-executable. So even if you put any code on the stack, you cannot change the return address to point to this code and then execute it. Now, in return to libc, you're not putting any code on the stack. Basically, you're changing the return address to point to an existing code, which is part of your libc. So even if you make the stack non-executable, the return to libc attack is still possible because you only reusing the code which is already part of your code pages. Okay, and the code pages are executable. The libc code is executable. It has to be executable. You can't make it non-executable, right? So the W XOR X does not prevent the return to libc attacks. Okay, here we are actually not here. The main point that you would need to understand is the return address is now pointing to a code which I mean to a code which is already part of your text segment. Like it is already part of the code that can be run. It's not code that your attacker is writing. The code existed in your program, okay? And you're just modifying the return address to point to this existing function. So that's why you're not writing any code on the stack. And since you're not writing in the code on the stack, even if the stack is not executable, return to libc is still possible. I hope it is clear. If not, then please ask me to repeat. Then the second question is about stack canary. And in the stack canary, the question is, does it prevent the return to libc attack or not? So how does stack canary prevent a buffer overflow attack? So the stack canary is let me just go, I think, to the slide. Give me a moment. I'll look at the slides if it's open. Yeah. So I think there is a course of this. Mm, okay, so I think the layout is a bit it's not placed correctly. But what I want you to focus here on is so first is the first point is the stack canaries are added. The code for the stack. What is a stack canary? So stack canary is actually just a random data. Okay, that is the first point. So stack canary is just a random data. And who is creating this data? That is the compiler. Okay, the compiler is creating this random data. And then it is placing this random data in the stack frames. And where is it placed? It is generally placed to prevent the return address. Okay, so that's why it's added below the return address. So with respect to your, maybe I think what I should be doing is to modify this only. Yeah. So this is your canary. Okay. This canary is actually placed by your compiler. So this is like compiler, as we saw yesterday, the compiler is going to add additional instructions in your program. And what it is going to do is when your new function is going to start, here the function foo is going to start, then when the function foo's this stack frame is created, then as after it has created the stack frame, that it is has set the eBPF value to top of stack, then it had some line of code where it was actually storing the value of canary into your stack frame here. So it is generally stored. So the stack canary for function foo, so to prevent the return address from the function foo, the stack canary is placed here in the stack frame of foo. So here we are placing a stack canary in the stack frame of foo. So what will happen is now if the buffer is overwritten, not overwritten, if you write beyond the bounds of the buffer, then in the process to change the return address, you would have changed the canary. Okay, you do not know that the canary, what is the value of the canary. So since you do not know the value of the canary here, you have because it's a random data which is generated at say runtime by the program, and it's randomized data, so it is changed every time. So the hope is that the attacker will not be able to guess what is the value of the canary, and therefore cannot craft this input to the program such that these particular bytes are set to the value of the canary. So what happens is that when the programmer tries to then overrun the buffer and change the return address, it would have corrupted, it would have changed the value of this canary. So let's say if this value of the canary was say 0x F2, then the attack, of course, it's going to be longer byte sequence, then it would have been changed. So now I think now what I should clarify here is that this stack canary is part of this function foo's stack frame. It is added by the compiler in the copy buff function itself. Okay, I mean it's added by the instructions for adding this canary are also part of the foo function, and the instructions for checking the integrity of this canary are also part of the function foo. And the integrity of this canary is checked before the return instruction. Okay, the that stack canary integrity is checked before the return instruction. And another thing is that the since we just looked in the beginning today that there can be other control data also, right? Like function pointers, or say the like they can be function pointers, or there can be say this control data like auth variables. So what we can do is that we can actually prevent those variables also from corruption, and the way we can do that is we can shift the canary bit down, and then we can say those variables like function pointers or something we can store here. So then if the attacker tries to corrupt this function pointer, then also the canary will be changed. and then it will not be that will be detected. So I hope that it clarifies the functioning of stack canaries. And so if you want, I can even show you the code where, like, for the stack canary, where the stack canary is there. Yeah, I think so. Yeah, of course, it is not a foolproof solution. So if the attacker is able to print the content of the stack, so there are some memory vulnerabilities which exist, such as the format string vulnerability, which we are going to discuss next. So if the attacker is going to exploit some other vulnerability, like including the buffer overread or something, and or if the attacker is able to guess the stack canary variable value, then it can try to craft a input in such a manner that the stack canary value remains uncorrupted. So for that, the attacker will have to inspect the content of the stack when the program is running. Okay. So we will also look at that. So I hope that this makes it more clear that the stack canaries actually prevent the write operations here. It is going to prevent the write operation, because if in the process to change the return address, the stack canary can get corrupted, and that can be detected by the by at runtime when the function is returning. The foo is returning to main. There is an integrity check for canary. So the answer is that stack canary, does they prevent return to libc attack? So yes. So if there is a stack canary, then it can prevent the return to libc attack, because in the return to libc also you are doing this buffer overflow exploit, where you are going to overrun the overwrite beyond the bounds. So you're writing beyond the bound of the buffer, and in that process you can change the canary. Now, does ASLR prevent return to libc attacks? So the address space layout randomization says that we are good that you can that at runtime, whenever your program is launched, whenever a process is created, every time the process address space is randomized. What does that mean is that every time your stack is located as a different address, like the stack base address is changed, the base address of your heap region or your text segment or your libraries where they're located. So these virtual addresses where your programs like the base address or something, they will be changed of these different segments. So what that causes is that your attacker may have crafted this say exploit, may be able to craft this exploit for a particular run of the process, but when the process will be run again, then the process layout would have changed. And then these addresses would have changed. And that is why you will notice that sometimes these demos that we are doing, sometimes they do not run because of address layout randomization, because the layout is changed, the sometimes the addresses are getting changed. So we have to again figure out what will be the return address. And ASLR actually prevents the so because of ASLR, it prevents the attack from like spreading actually. So if there is no ASLR, like address layout randomization, then if you're able to do an attack on your machine, and if you send that exploit string to on the web to on the network to other machines, then that will actually work on all the machines, because if the process layout is fixed. But what ASLR provides is that even if you're able to create this exploit, it may work on some programs, but it may not work on a majority of the systems, right? So it is not a foolproof solution. Like it is again a probabilistic randomization based solution, but it is still provides like can prevent the return to libc attack if the address space has been randomized. Yeah, so it makes it more difficult to exploit. Stack canaries also make it more difficult to exploit. Okay, if you use some other vulnerabilities to inspect the content of the stack, again, like the stack canary can also change at every run of the program. So again, that is also makes it difficult to exploit. And the W XOR X here in case of return to libc basically does nothing. So we are not even executing anything from the stack, so it does nothing. And even if W XOR X is present, the return to libc attack is going to work. So, so the crux is that if W XOR X is present, then return to libc attack will work. It will not, there is no problem at all. If stack canary is present, then it may or may not work, because like may or may not work means that if the attacker is able to guess the value of the stack canary correctly and able to create this exploit, then it may work, but there is a high chance that it also doesn't work. And similar, and then for the ASLR also, it may or may not work, depends on the layout of the process address space. So I hope that makes it clear and also puts all the defenses and everything that we have discussed so far in context. And now, since so now let's so maybe I can just stop for a while, and if you have any question till this point, then you can ask me. So I hope that the pace at which we are going is not too fast, and I hope that the repetition is making things more clear. If you want me to, if not, if something is not clear, or if you think that I am, if I'm going too fast, then please let me know, so that because it's important, because when we are first looking at these attacks or these vulnerabilities, it takes some time. It can take some time for us to even understand these things, and especially that we are now looking at so many different attack and then defenses, and then comparing whether one kind class of attack can be defeated with a defense or not. So feel free to give your feedback as to whether I should reduce the pace or repeat something in the chat box, and feel free to put your questions if anything is not clear. And but what I want is that the end of the day, when we have, say, looked at all of these different classes of attack, what we should be able to do is, I think, let's see if I can. Okay, what I was saying is that at the end of the day, once we have looked at all of these different classes of attacks and defenses, what I want is for us uh, to be able to tell that which class of attack can be prevented with which defenses, and of course also that uh, are these defenses like OS based or compiler based, etc. So, and how to, and a overall idea of like how the defenses are going to work. So just give me a moment. Yeah, so this so at the end of I think that at the end of today, we would have covered these different kinds of memory exploits and also looked at these different defenses. So then at the end of today, you should be able to fill this table. Okay. Uh, like you would have learned about these different defense techniques, you would have learned about these different memory exploit types, and then you will be able to answer that which of these defenses can prevent which of these attack sequences. So you can fill this table, and I think that will be a very good summary of what we have discussed, what we would have discussed in these 2 days. Okay, with that, actually, I would like, if there is no question, then I would like to continue with ROP attacks, and we will do it only for the next half an hour. And after that, we will take a break for lunch. So I may not be able to cover everything before we take a break, but that's okay. Then when we come back, then we will continue again. So, return oriented programming, ROP, in short, is actually so is actually why are we now discussing ROP? Why are we discussing a new class of attack? Because when we were looking at this return to libc attack, we saw that there is a limitation here. And the limitation is what? That the attacker can only call certain functions in the library. So the library, let's say, has, I don't know how many functions are in the library. Of course, there are enough, like many functions, maybe thousands of functions in the library. But still, the attacker is restricted with these certain functions in the library. And if these functions, let's say some function is removed from the library, then that function is no longer available to the attacker to use, right? But what if the attacker wants to do something arbitrary, like some arbitrary operation? Yeah. So what if the attacker wants to do some arbitrary operation? So that is the power given to the attacker with return oriented programming. So return oriented programming is actually a very powerful attack technique, and it's like of it has been earlier. I think earlier these classes of attacks like return to libc and return oriented programming, they were thought of as not very, like they were thought of that they are not so feasible. But in recent years, actually there have been like more work in these directions, and now they are considered to be a feasible uh, attack technique. And so the return oriented programming we are going to look at now was actually discovered by Howard in Stanford University. And so as in a regular return to libc attack, we what it does is that it subverts the execution to the library function in the libc, and it can be used even with a non-executable stack, since the instructions are actually legally part of the executable that you are executing, right? So unlike the return to libc function, the return oriented programming here does not require to execute certain functions in the library. Okay. In fact, with return oriented programming, an attacker can do and run any arbitrary code. Basically, even the code which does not exist in your program. Okay, so I would emphasize on this again, that with return oriented programming, the attacker has the power to execute any arbitrary code into your program, any arbitrary code, basically, even the code which is not part of your program. And the attacker is not going to write that code on the stack also. It's not going to write that code. It's going to generate that code from the code which is already present in your uh, program. Now, if you're interested in learning more about this, then you can read this paper, uh, The Geometry of Innocent Flesh on the Bone Written into libc without function calls, okay, on the x86. So I'm sorry. So let's say that this is the payload which needs to be executed on the attack by the attacker. Okay. So yesterday we had looked at, we were saying that, okay, we want to execute the shell. And then in the slides, we had looked at this uh, list of assembly instructions that we would need to invoke a shell. So similar to that, let's say that the attacker wants to execute this payload, like he wants to execute these instructions into the uh, as part of the payload. This is the target payload. Now let's suppose that there is a function in libc which has this exact sequence of instructions. Then we are actually done. We can just change the return address to point to the start address of this instruction. Okay, so if libc has a function with the exact same set of instructions, with the same in sequence of instructions, then what we are going to do is that we are going to change the return address on the stack, and then we are going to point that return address to this address. We're going to change it to the address of this location, the address of the first instruction in this sequence. Now, what if such a function does not exist? What if this sequence of instructions does not exist in your program anywhere else? Then what can we do? So the attacker here is actually very clever, and the attacker is like, okay, if I cannot find this sequence of instructions into the program, then let me build it. So let me go and build this attack sequence, the sequence of instructions. So now we are going to see like how the attacker is going to build this sequence of instructions which does not already exist in your program. So again, to repeat, the attacker is interested in executing this sequence of instruction. Of course, the first, yesterday we saw that we can put this attack sequence on the stack and then we can execute it from the stack. But that is not possible if we have W XOR X enabled, if we make the stack non-executable. So then we are talking now about return to libc kind of attacks, where we are not going to run anything from the stack. We are going to change the return address to something which is already part of our program. Okay. We like today we just looked at the to libc attack where we had changed the return address to point to a function in libc. But what we are saying now is that it is possible that what the attacker wants to do is actually not, there is no function in libc to do that. There is no function in libc with this attack sequence as it is. So then what can we do? The attacker can actually create this attack sequence from the instructions which are already like part of the your program. Now how to do that? So so to do this, we are going to create something called gadgets. So what is a gadget? So gadget is a short sequence of instructions followed by a return. So it's very important to emphasize that there is a return instruction in the end. So a gadget is a short sequence of instructions followed by a return. And the the useful instructions here, which are like marked here, these instructions should not transfer the control outside the gadgets. So the only way you can get out of this gadget is by doing this return. Okay. So after that, so what it will become more clear as we will look at the example, like what is a gadget. For now, you can just remember the definition of a gadget. So it's a short sequence of instructions followed by a return. And it should not pass control, it should not transfer control outside of the gadget. Okay. And how do we find such gadgets? So to find such gadgets, actually, we can do the binary analysis. We have the program binary. We can statically analyze this binary. Basically, we can analyze the libc, okay, in this case. And as a pre-processing step, we can, because the libc is what libc is available, like it's open source, so anybody has access to the libc and the libc binary, so anybody can analyze this libc binary, and then they can try to find such gadgets. Okay, I think I'm not able to move the this, so let me. Okay, so is there any question? Mhm. Okay, so the first step is to find the gadgets. Okay, here. And a gadget is a sequence of instructions followed by a return instruction. And we can find such gadgets by doing a binary analysis. That's what we are saying. Now let us look at these gadgets. What are these gadgets? So a gadget, as we just said, is a sequence of instructions followed by return. So these can be, say, the gadgets. So like, for example, you want to do this, this is your payload. Okay, the first instruction is move LESI, comma 0x8 ESI. So this is your instruction, and then you will do a analysis of the binary, and then you're going to find, is there any place in your binary where this instruction exists, followed by a ret. So you may be able to find with binary analysis, let's say you find some location where this instruction is there, move LESI, comma 0x8 ESI, and it is followed by ret. So this is will form your gadget 1. Similarly, for the next instruction, let's say you find this gadget, then third gadget, and then the fourth, and etc. So this you are going to find by doing the binary analysis of the analysis of the binary. Now what you are going to do is that you have to stitch together these gadgets so that the payload is built. Like first you have to invoke the gadget 1, then you have to invoke gadget 2, then 3, then 4, etc. So that, like, basically first you have to start here. Then when it returns, then this return address should be the address of gadget 2. When the gadget 2 returns, it should return at gadget 3. When gadget 3 return, it should return at gadget 4. Okay, so this is your, these are different gadgets, let's say, that you have found into the program binary, and then you have to stitch together the gadgets. So how do we stitch together the gadgets? So the return instruction here is the instruction we are in, like, is of interest. So the return instruction has these two steps. So the first step is to pop the content pointed to by ESP into EIP. So your when your function is returning, at that time, before the return instruction executes, your ESP is actually pointing to the return address on the stack. And your return instruction is going to take that content which is pointed to by the ESP and store it into EIP, where EIP is your instruction pointer. After that, your return instruction also increments the ESP by 4 on when we are talking about a 32-bit machine. Okay, so your ESP is incremented by 4 bytes also. Now, how are we going to lay out the stack to stitch together these gadgets? Okay, so let's say your ESP, when you are, say, in your function foo, and when your function foo returns, let's say the ESP is pointing here. This is the start of, this is the location of the return address on the stack. And then you are going to change this return address with the address of gadget 1. And then you are going to Of course, using the same buffer overflow, you are actually in with the buffer overflow. Initially, you're writing the garbage value, but once you start writing, then you find the return address location. You first here write the address of the gadget 1. Then you will add here the address of gadget 2, followed by address of gadget 3 and gadget 4. And if there are more gadgets, then so on. Okay. So what will happen is when your function foo returns, it's going to take the address of gadget 1 from, it is going to take this address and store it in the instruction pointer. Okay. And then it is going to increment value of ESP by 4 bytes. So then the ESP will point here and your program counter program flow would have changed to gadget 1. So gadget 1 will execute. Okay, then the next, when the gadget 1 is going to return, again your ESP is now pointing here. Okay, and at that time it is going to read this a byte sequence which is stored here as the return address, store it into EIP, and then it is going to transfer the control to here to this gadget 2. Afterwards, when gadget 2 returns, again it is going to pick the next bytes as the return address. Sorry, yeah, next byte as return address, and then it is going to change again the instruction pointers, start executing gadget 3, and so on. So this is how you are going to stitch together the gadgets by putting the addresses of these gadgets in the order that you want to invoke them on the stack. So is there any question? Is it clear so far what we have discussed? So how is it different from return to libc? It's different from return to libc because now you are not actually creating and calling any particular function. Here you are able to create a sequence of instructions. Okay, and for doing that, you are doing this analysis of the binary and creating these gadgets, where a gadget is a short sequence of instructions or useful sequence of instructions followed by a return instruction. Okay, and this sequence of instructions should not transfer the control outside of the gadget except at the return instruction. Okay, so if there is no question, then actually I will look forward. Yeah, so it's actually very, yeah, it's comparatively uh, complex attack to do, because then you would have to do this find these gadgets, and then you would have to stitch like you will have to find these gadgets, then you will have to find the address of every gadget, right, by doing the analysis of the binary at runtime, and then you have to put the addresses on the stack like this. So it's a more involved and more exotic kind of an attack, which is like harder to do. And this class of attack is actually also popular with the name code reuse attack. Okay, so it's popularly known as code reuse attacks. Because we are reusing the code which is already present in the program binary, right? We are not adding any new code here. We are reusing the code which is already present. So this type of attack, return oriented programming type of so actually return oriented programming I should say is actually a subclass of code reuse attacks. The code reuse attacks are actually they would not they have more other different kind of attacks. But it is also a type of code reuse attacks. Okay, so I think so far everybody is able to follow what I have said about return-oriented programming. And so let's look at the next slides. Uh, okay. The first step here is finding gadgets. Okay. So as I just said also previously, that to find these gadgets, we are going to do the static analysis of libc. Now to find the gadgets, we are going to do the binary analysis of libc, and what we are going to do is that we need to what we need to find. We need to find a set of instructions which is ending in ret. Okay. Yes. So the significance of ret here is so that the attacker can stitch them together, because then the attacker can put these return addresses on the stack, and whenever a gadget will return, it will be able to it will take the next 4 bytes, which it will take the address stored actually at the ESP as the address of the next instruction to execute. So the significance of ret instruction here at the last, as the last instruction in every gadget, is so that the attacker can put these addresses of the gadgets on the stack, and every time a gadget will return, it will return to the next gadget. So here. So first, we put the address of gadget 1 when it will execute, and this return instruction is executed here. Yeah. So when this return instruction is executed, the return instruction is going to take the address of, is going to look at this location, uh, and it is going to think that this location contains the return address. But in fact, this is the address of the gadget 2, which has been placed here by the attacker. And then it is going to take this address, and then it is going to use that as the instruction pointer, like to as the return address. So that's from where it will start executing. And will these gadgets have the ret at the end? Yes. So that's a condition. So that's the definition of a gadget. So a gadget is a short sequence of instructions followed by a ret. So it is the definition. By definition, anything. If it doesn't contain a ret in the end, then it's not a gadget. So it has to end in the ret. I hope that answers the question. And so now, moving forward, we need to find these gadgets. What do we need to find? We need to find a set of instructions that end in a ret. Now in the x86, the ret instruction opcode is 0xC3. Okay, and now we will come to this in a bit, that the instructions can be intended or unintended. We'll just come to it. And the second condition is that besides the ret instruction, none of the instructions should transfer the control out of the gadgets. So there are these two instructions. Sorry, there are these two conditions for a gadget. First condition is that it should end in a ret. Second condition is that none of the instructions should transfer the control out of the gadget except the ret instruction. Now, how do you find a gadget? So actually, if you will go and look at the paper, which is here, this paper written into libc without function calls, this paper actually has proposed this algorithm to find these gadgets. You can go and look at that if you're interested. But in a very simplified way, what how the gadgets will be found is by doing the binary analysis. So we are going to find the occurrences of return instruction. So the return instruction, as I just said, is just this C3. This is C3 represents the return instruction. So we are going to find the occurrences of C3, and then we are going to look backwards actually. So we are going to look backward. We are looking backward, and then we are going to look at byte by bytes here. So we are going to look at this byte, and then we are going to check whether if I use this byte and then followed by this like the byte sequence like C3 3C C3, does it correspond to some valid instruction? If it corresponds to, say, a valid instruction, like, say, something ending with ret, if C3 is some other instruction, then we will actually store that as a valid gadget. So what we are going to do is, in this pre-processing step, here actually we are trying to find all the gadgets which exist in the library. Okay, not only the gadgets that we are interested in, that we looked in the text sequence, but all the gadgets that are in the libc. So I think there was the paper they had they were able to find out 15,121 such uh, nodes, like such gadgets in this libc library. Okay, so the when this return opcode is found, then we are going to start scanning backward. With each byte, we are going to ask the question if the subsequence forms a valid instruction. If yes, then we are going to add this subsequence as a valid instruction in our like like the this data structure. So here the try data structure is being used to keep track of these gadgets. So this byte sequence is added as a child there. If no, then we go backwards until we reach the maximum instruction length, that is 20 bytes. And then like basically we will stop there, and then we will start scanning again to see if it form the next bytes form a sequence. And then we are going to repeat this until length w, which is the maximum instructions in the gadget. So let's say we have a definite we have a limitation on how many instructions can be in a gadgets. So where then we will stop if, say, we have found the maximum number of instructions that can be in a gadget. So in so basically, simply what we are doing is that we are going to locate these C3 byte sequences, that is the return instruction opcode, and then we are going to scan backwards. And when we are scanning backward, then we are going to check whether the subsequence forms a valid instruction or not. If it forms a valid instruction, then we are going to store that as a gadget, and then we keep searching. So I hope this is okay. Uh, of course, this is simplified version, and you can find the full algorithm on finding gadgets in the paper. Now, there are these what we are making a distinction between unintended and intended instructions. So what are intended instruction? So intended instruction sequence means that the machine code intentionally put by the compiler. So the compiler has actually intended to put those instructions in the code. Okay, uh, an unintended instruction sequence is that what the we can interpret the machine code differently in order to build a new instruction. So this will become a bit more clear with this example. Is, say, this is the machine code. Okay, this is the machine code, which is F7C70700000000F9545C3. So this is the machine code. So actually I will stop after this slide. Okay, so this is the machine code F7C707000000F9545C3. Now, what the compiler intended to do was this. The compiler intended to like treat like what the compiler intended to do is that these machine code corresponds to these two instructions. Basically, when if we start interpreting this byte sequence from F7, then F7 C7 07000000. This byte sequence here corresponds to this instruction test hexadecimal value 7, comma EDI. And then 0F9545C3, this byte sequence is corresponding to this instruction set NZP minus 61 percentage EBP. Okay, so this is what the compiler say intended to put in the code, machine code. But what was not intended is that if you just shift by 1 byte, and if you just start interpreting this machine code from C7, then you can obtain a different set of instructions. If you start interpreting it from C7, so C7 0700000000F, this byte sequence actually corresponds to this instruction move L 0x0F and followed by all zeros EDI. 95 correspond to exchange instruction EBP, EAX. 45 is say increment EBP, and C3 is of course your ret instruction. So here, as you can see, even though return instruction was not present originally into this byte sequence, we had since started interpreting, like we had started looking for gadgets from the backwards here in this machine code. We said, okay, C3, let's say it's ret. Now, 45, it's let's say INC EBP. 95 is opcode for exchange. And then this byte sequence is the move L instruction EDI. So uh, that's what we are going to do. That is basically what is done with the binary analysis. So the machine code is checked back from whenever we find a C3 occurrence, we are going to reverse check it, and then we are going to construct these sequence of instructions. And of course, this is just one example. It is possible that maybe 9545 would correspond to some other instruction, or there will be some other instruction. So it's very this is actually highly likely to find such diverse instructions of this form in the x86, which is the CISC architecture, because it provides a variety, like it provides diversity of instructions. That is the first thing. Second thing is that in x86, the instructions are not of fixed length. Like as you can see here, this instruction is of how many 6 bytes, this is 4 bytes. And so that also gives us the flexibility to interpret the byte sequences as different in a different manner. In contrast, RISC processor ISA is more simpler, and it's not so likely to have these different diverse instructions. Also, the RISC processors have a fixed length instructions. So like the instructions are 32-bit. So every instruction is 4 byte. So that's why even if you start from say C3, you have to interpret the next 4 bytes. You have to take the next 4 bytes as an instruction, then only the next 4 bytes. So that gives the attacker, that reduces the flexibility that the attacker has to find these byte sequences, valid byte sequences as instructions. But having said that, it is not impossible to do it on RISC, although it is less likely to do a ROP kind of attack on a RISC processor compared to a CISC processor like x86. So now here I will stop, and if you have any questions, then you can leave them in the chat box, and we will come back we will start at around 2:10. And so if you have questions, then please feel free to leave them. Otherwise, you can uh, you can take a break now. Why for gadget? Second condition, no control flow. of ret is important. Mm. I actually don't understand the question. Okay, so I understand it now. So you're saying that why is that the case? That the second condition which we discussed here, that the no that the control transfer out of the gadget should not be possible. Yeah, that is because if uh, if that if that is the case, if the control transfer can happen, then we no longer have, then we will no longer be able to stitch them together as we want. Let's say if the if you have created a gadget such that the gadget can transfer control somewhere else, then the attacker loses the flexibility to to call another uh, instruction of the attacker choosing. So basically, having a gadget which does not transfer control out of the gadget except at the return instruction gives the attacker the power to invoke next the bytes, the sequence of instruction of attacker choosing, because then the attacker can put the address of those that next gadget on the stack. Okay, thank you very much for the question. Uh, I will stop the recording. Is there any way to scan for this attack? Yes. So you asking, are there any ways to prevent this kind of attack? Yeah. So to detect this kind of attack and prevent this attack, we have CFI, control flow integrity, which we are going to look at. We are going to look at the control flow integrity defense uh, later today, and also we have these control flow attestation techniques, uh, which will probably look tomorrow. Yeah, so we will look at the defense. Okay, thank you everyone. I'll stop the recording and we will meet around 2:10 or 2:15.